Hello everyone and welcome back to part 2 of Verlet Integration implementation. In this part we'll be talking about the simulation of single point motion. I'll be showing you an example of implementation that you can use to implement basically what you can see here, the motion of a single point or a ball. So let's get down to explaining how this is going to go. So let's say this is the display. All right, this is this black square is our display screen. And let's say that we have a ball or a representation of a point, and we need, in order to simulate the movement or the motion, we need actually to figure out the curve that it's going to move by between two certain positions, right? So now let's say that we have a discretization of a step dt, meaning that between two frames we have delta time equals to dt. All right, so now we've seen in the previous part that we can use a variety of integration methods, one of which is Euler's method. So basically Euler's method, we need to know what the speed at every time step is in order to figure out the next position of the point. So we have xn plus 1 equals to xn plus the velocity at time step tn times the dt. All right, but we're not going to be using this because let's just say that we don't know how to compute the speed, and basically we don't have a fixed speed because our speed in the example we'll be doing depends on the previous position and the current position. So here in Verlet integration we have two positions basically: the old position xn minus 1 and the current position xn. So, and we need to figure out what the next position xn plus 1 will be. So basically what the algorithm tells us is that xn plus 1 depends on xn minus 1 and xn, and it's equal to 2 times xn minus xn minus 1. So this is exactly what we'll be using today to simulate the movement of the particle. So get yourself a cup of coffee and let's get down to coding. So before anything I should mention that we're using Python here and pygame to implement this example. So the first thing I'll be doing is implementing a point data structure that will hold our x and y coordinates and the old x and old y coordinates, as well as a radius that will represent the ball basically. So you notice that in the Verlet algorithm we do not use the speed but rather have old x and old y. So this we need to return a dictionary that basically has keys that are coordinates with value x and y, and another key that will be old coordinates, old chords here, that will hold the values of old x and old y, and note that these coordinates will be stored as lists, as well as the radius under the key of string r and the value r. Next we need to define the function for movement. So movement function, so it will be def move p of p basically. What we'll do here is, first of all, we need to get the coordinates let's put them in a variable. Chords equals p of basically value of the key chords. Second, we'll need the old coordinates, basically. Old chords equals p of old chords, basically. Let me just do that here. And first we'll need to compute the velocities, basically. So the velocities is, as you notice, will be basically it's not really a velocity, so to speak, but it's just an update rate. It's like what the value that will update our current positions with. So let's name it a v, which will be a list that will hold vx and vy. Vx will be computed as the coordinates of 0 minus old coordinates of 0. Basically, it's x minus old x. And vy will be y minus vy, so minus old y. Sorry, so it's chords of 1 minus old chords of 1. Next, we'll be updating the old chords, the old coordinates. So we'll do p of old chords, and we'll be setting it to the current position, because now we've already computed the velocity vector, with which we'll be updating our current position to get the next position. And so we don't need the old chords anymore. We can just set it to the current position. And now we need to update the current position. P of chords will be equal to, so it's gonna be a list, basically, and we're gonna make it chords of 0 minus plus v of 0, so plus vx, and coordinates of 1 plus v of 1, so it's vy. Now we'll need a function to render this, what we've just coded. Let's just go ahead and implement a render p function that will basically just draw our ball. And to do that, we'll need first to import pygame, because we'll be using pygame to display the ball. So we're gonna import pygame, and we'll need to create a variable for our display surface. This will be display equals pygame.display.setMode and setMode, and let's just set it to a 500 by 500 window. All right. Okay. Now let's go ahead and write our render function. So in the render function, we'll do pygame.draw.circle of, basically it takes the display as arguments. It takes display, color, and coordinates for the center and the radius. So the color will basically be a tuple. Let's just set it to a greenish blue. So we'll do color equals the tuple of let's say 100, 255, and 200. Let's just do that. Okay, so the center is going also to be a tuple, and it needs to contain the coordinates for the p point. So it's going to be p of 0, or of chords of 0, and p of chords of 1, basically. P of chords of 1. Okay, and the radius is going to be an integer, and it's going to be p of r. Make sure that the p chords of 0 and p chords of 1 are integers, or else it's going to give you an error. So now we need to write our loop that will actually display the display surface. Let's call it simulate p of point. It will take p as an argument. So it's pretty much generic code for pygame here. Clock equals pygame.time.clock. It's going to return a clock object here, and we define a stop condition variable. stp equals true. So while stp, we'll go ahead and fill our display.fill. I'm gonna choose a gray color, I believe. It's 25, 25, 25. Yeah. And now we'll need to define the stopping condition for event in pygame. In pygame.event.get. What we'll do is it tests if event.type is equal to pygame.quit. So it's just generic code, as I said here, for pygame. Pygame.quit, capitals, quit. And we'll do stp equals false. So basically we're telling it here to, when you click on close the window, you're gonna set stp to false and stop the loop, the while loop. And next we need to do pygame.display.update in order for it to update the display surface. And we're gonna tick the clock. Let's do here 5, just so that we have a slow movement, so that we can see it. And next pygame.quit in order for us to close the actual window. So inside this loop, we'll need to call the move p function and the render p function, starting with the move p function, obviously. Move p of p and render p of p. Alright, and next we're gonna have to call the simulate p, but before that we'll need to define a point. So we're gonna go ahead, p equals, as we defined it, point underscore, I guess, yes, it's underscore, of, and let's just give it 100 by 100 x, 100 y, and as previous position 95, 95, and radius of 10. Now let's call the simulate p function, and let's see what that looks like. So as you can see, so the ball is moving slowly on the screen, but as you can see there, we didn't have any forces or anything, so the ball is not bouncing off walls, it's not reacting to gravity or anything. So now we're gonna go ahead and add some forces, starting with gravity. Let's set the gravitational constant g equals 9.81, and a friction variable, we'll set it to just below 1, 0.95 something. So adding the forces actually is just simply incrementing the speed. So for the gravity, we need v of 1 there. V of 1, we need to increment it by g, basically, so that at every frame the y position is incremented by g, which corresponds to having acceleration. So v of 1 plus equals g. And for friction, we need to multiply the speeds by the friction. So you can do it while incrementing the p chords or here. I'm just gonna go ahead and do it here instead. So v of 1 times equals friction, and v of 0 as well is going to be multiplied by the friction. V of 0 times equals friction. So now basically you need to see a faster movement downwards. Let's go ahead and add some collisions with the sides of the display. Okay, let me explain here a bit of physics and how we're gonna do this. So let's say this is our display as usual, and let's just take here, by the way, the explanation I'm about to give is inspired by coding math. He did a great video on this. Make sure to check it out on his channel. So let me just go ahead and turn off this grid. So basically, this is the lower border of the display. Let's take our ball. It's going to be moving downwards towards the border, but as it approached it, we noticed that the y value is larger than the height of our display surface. So how do we actually proceed? So first of all, we're going to set the y value of the ball to be equal to h. So y equal h. This is going to be our new current position. It's the current position for the algorithm. And next, basically, this position is no longer going to be considered in the computation. Well, actually it will, but not right now. So this is the old position now, and this is the current position that we'll be incrementing to compute the next position. So for which y is equal to h. So let's take the old position. So you would think that this is the Vy and the Vx. Well, basically this is the Vx, but the Vy is still equal to the older value, meaning it's still equal to the y on this position minus the old y. So basically this is the reference for Vy that we'll be using. So this, let me choose another color. This here is Vy, okay? So basically here what we'll be doing is we'll be taking this Vy and Vx, right, and adding it to our current position. So we're gonna take the current position, which is Vy, the current position, that's right. So the y on the current position, and update the old position by setting it to the current position's y plus Vy. So this is how actually the Verlet algorithm works. Instead of trying to figure out the speed for your own, it's defined by the old position. So if you change the old position, the new or the future position is basically going to change. And this is just an example here where we are going to set the newer value for the old position, the y value for the old position. We're going to set it back to h plus Vy. So it's h plus Vy. It's no longer the old value for old y. So, and this will give us a future position that will basically make it look like the ball bounced off the wall. Alright, I hope that was clear. For any questions, please make sure to ask your questions in the comments. So, after having explained how the collisions will be handled, let's go ahead and implement that. So we'll define a new function. Let's call it collide p. It's going to depend on p. It's going to depend on p and also on the width and height. So okay, let me clear this up. So we need first of all to recompute the velocities. Let me just grab them from the previous function. Here we go. And after having computed them, basically we're going to test if our position is bigger than the width and height or smaller than 0. So first of all, let's set the w, which is the width, to the width minus the radius, because here the ball has a radius, so we're gonna say that the ball has extended the borders if its center has extended the radius of the ball. Same thing goes for the height. So now if P of chords, or just chords of 0, let's go ahead with that, chords of 0 is larger than W, what we'll do is, as we said, we'll take the P of chords of 0, we're gonna set it to W, and basically we're gonna set it to W, sorry, and basically we're gonna update the old chords. We're gonna update it with the current position, which is W, which is P of chords of 0, or yeah, P of chords of 0, which is just simply, it's equal to W plus the Vx. And the same thing that we explained for the y-axis. So if it's superior to h, if a chords of 1 is superior to h, we're going to take the P chords of 1 and we're going to set it to h. And we're going to update the old chords of 1 to be equal to the P chords of 1 plus Vy. And now for the conditions with the 0 borders, it's basically going to be the same thing. Let's copy that. Okay. So this time the condition is chords of 0 inferior to the P of R, the radius of the ball. So if it's inferior to the radius of the ball, we want to set P chords of 0 to the radius, which is P of R, and the computation or the update of P old chords is going to be the same. And now for the y-axis, it's going to be P of chords of 1 inferior to P of R, and we're going to set it to the radius, and the update is going to be the same. So now we also need to call the collide P function in the simulate P. Here we go. So we're gonna call it right after the move P function. So it's gonna depend on P, W, and H. So the W and H need also to be arguments of simulate P. Here, P, W, and H. So now in the call of simulate P, we're gonna add two new arguments, 500 and 500 for our screen. Let's see how that looks. So now you can see that the collisions are handled. Okay, so now we want to set also the interactions with the mouse. Basically, here's how, just an example of how we can do it. You can do it your way. So here I'm going to see test for a condition of left button mouse button press if pygame.mouse.get pressed of 0. That's the condition for left mouse button. We're going to take the position, we're going to define a new variable pause equal to pygame.mouse.get pause, and yes, that's going to return a tuple. So we need to make sure that we don't directly assign it to the position of P, of the point. So instead we're going to go ahead and do P of chords. We're going to set it and we're going to create a list which contains pause of 0 as the 0th element and pause of 1 as the element at index 1. So now let's go ahead and run that and see what it looks like. So here the ball responds to our mouse input, and we can even drag it and let it go, and it will launch at given direction. So yeah, that's basically will be it for this tutorial. I'm gonna show you here a funny thing I made using the same thing. Try to implement it yourself and tell me what you think. So here I just randomize the sizes of the balls, and I randomize the initial positions, and just I created a function that basically simulates a group of balls instead of just one ball. So yeah, you can do the same thing, or I don't know, instead of constraining the balls to the same rectangle, you can use different constraining functions. So thank you so much for watching. In episode 3 or part 3, I'll be talking about rectangles and how to implement them. So I'll just give an example of constraint function.